Hi guys, welcome back. Today we will go over belt friction, and I have done this problem before, and the reason I'm doing it again because I've noticed a few weeks ago that that video that I posted was about 30-second long, and I don't have any video that is that short. So I looked at it and it was just pitch dark, no image, no sound. So somehow I was able to mess that up. So today I'm going to redo that video with the same problem, but this time hopefully it's going to have an image and it's going to have some sound. And yeah, hopefully it's going to work. Another thing that I want to add is that I wasn't able to fix that pen problem that I had last time. So I have managed to do something else this week, and hopefully you're going to be fine with that. As always, if you're new to my channel, I want to encourage you to subscribe and give it a like if you do like the video, because this helps put this video in front of more people just like you. Okay, that being said, I think we're ready to move on. A fixed and a movable pulley are used to support a load of 120 kilograms as shown. If the pulleys are assumed to be massless and the coefficient of friction between the rope and the pulleys is 0.10, what is the minimum force F necessary for static equilibrium? So the first thing I would like to do is go to FE Handbook. And of course, I already wrote that down. But what I wanted to say is, let's say you didn't know how to find this. Let's say you're on the exam, you have this problem. So the first thing you do, it's very easy. Just write belt friction, and it's going to direct you here to this formula where F1 equals to F2 multiplied by E mu multiplied by theta. And then lower you have explained what each coefficient is. F1, F2 are the forces, mu is coefficient of static friction, and theta is the total angle of contact between the surfaces expressed in radians. So here you're told it's expressed in radians, which is great. So I'm gonna show you what theta is. And now let's talk about F1. So F1, here it says force being applied in the direction of impeding motion. And F2 is force applied to resist impeding motion. What that means and what you have to remember is that always F1, I mean, not F1, it can be the other way, but F1 is the greater force, and F2 is the smaller force. And this is easy to figure out because F1 is equal to F2 multiplied by something. So that means that F1 is greater than F2. Perfect. Now let's go back to our problem, and let me show you what theta is. So here you have this little drawing, and instead of theta, this shows alpha, but imagine it's theta. And as you can see, this angle, theta, in our case alpha, is the angle formed where the rope is tangent to this pulley. F1 is tangent here, and then F2 pulls all the way down. So this is the angle theta or alpha. I mean, it's theta in the formula, so that's why I'm saying theta. Imagine if force F1 would pull this way, perpendicular to force F2. The point of tangency would be here, this point. So this angle alpha, or theta, it's going to be 90 degrees. Or imagine if F1 pulls all the way down parallel to F2, your angle alpha or theta is going to be 180 degrees, or expressed in radians is going to be pi. All right. So that being said, I think we're ready to just go ahead and write this formula down in our problem here. So I'm going to do that. F1 equals to F2 multiplied by E mu multiplied by theta. E power mu multiplied by theta. So let's adapt this formula to our situation. Or let's imagine, how can we adapt it? Which one is our greater force? Which one is our smaller force? Since the problem says that we have to pull on this side in order to have this system in static equilibrium, that means that the system is going down in this direction. Okay, so the system goes down here, and we're going to have a force here, F3. I noted here F2, and I left this F1. So F1, F2, F3, and the system pulls down this way, which means that F3 is going to be greater than F2, and F2 is going to be greater than F1. And the reason is, again, if you imagine that this pulls down in this direction, and we are asked to only pull on F1 so that the system stops. We're not pulling in F1 direction, right? The system never goes down in this direction. We're just stopping the system. The minimum force required to make the system stop, which means this is the minimum force. And then the bigger force is F3, and then next is going to be F2, and then F1. So we're going to write down F3 is greater than F2 and is greater than F1. And I hope it makes sense why. If not, leave a comment below, please. I'll try again next time. Okay, so now that we know that, we can apply this formula found in the FE handbook. So we're going to say that F3 is equal to F2 multiplied by E power mu theta. And we're going to also write that F2 equals to F1 multiplied by E power mu multiplied by theta. And now let's calculate this E power mu multiplied by theta, because we have mu given in the problem as 0.10. And theta, figuring out from this system here, our theta is going to be 180 degrees. Expressed in radians, this is going to be pi. So let's do that. I'm going to move forward from this formula here. It results that F3 equals to F2 multiplied by E power 0.10 multiplied by pi. And if you do the calcs, use your calculator, of course, you're going to get that F3 equals to 1.37 F2. And same thing at the bottom, we're going to have F2 equals to F1 multiply same thing, 0.10 multiplied by pi, and this gives you F2 equals to 1.37 multiplied by F1. Very good so far. And now let's see what can we do moving forward, because we only have two equations, and as you can notice, we have three unknowns. We have F1, we have F2, and we have F3, so we're not able to solve this. So now moving forward, we're going to look at this system. We're going to look at this system, and we're going to write from the free body diagram, we're going to write the equilibrium equation from this system. So we can say, if you look at this part right here, we can say F2 plus F3 is equal to 120 kilograms, or the weight of this, which is 120 multiplied by gravitational acceleration. In other words, F2 plus F3 equals to the weight of this block. So let's write that down. So free body diagram, we have F2 plus F3 equals to the weight. And I have down here calculated the weight, 120 kilograms multiplied by 9.81 meters over second squared. A note I want to make over here in regards to the weight or the mass. Sometimes students get confused and they don't know which one to use and when. In here, it's what I want you to notice is that you're working with forces, and the unit for the force is newtons. So if you use kilograms here, you're not going to be able to have a common unit. So that's a clue for you to realize that and instead of using 120 kilograms, you have to transform that and bring it to a Newton form. So that's where you do this, or it's telling you that you have to calculate the weight because 120 kilograms is the mass. So the weight is going to be equal to the mass multiplied by g, which is gravitational acceleration, So we have 120 kilograms multiplied by 9.81 meters over second squares, and this equals to 1177.2. And guess what? These are newtons, because kilograms multiplied by meters over second squared is equivalent to newtons. So that being said, we're good here. Now, what can we do with that? Well, we have F3 expressed as F2 or as weight minus F2. So we can come back to this equation that we have here and substitute F3 with this value over here. So let's go ahead and do that. We're going to substitute this in this equation. So F3, which is 1177.2 newtons minus F2 equals to 1.37 multiplied by F2. And this, moving forward, is going to be, we're going to take F2 from here, so from this side, and move it on the other side, and it's going to become plus. So it's going to give us 2.37 F2 equals to 1177.2 newtons. And from this equation, you calculate for F2, and F2 is going to be 4.96.7. Of course, you do 1177.2 divided by 2.37, and this is going to give you 496.7. Okay, very good so far. Now we have F2, and it's becoming pretty easy from here, because since we have F2, of course, we can come back to this equation and we can calculate for F1. And F1 is the force we need, because it's the force that we have to hold on to make this system be in static equilibrium. So we're just going to not pull down, we're just going to hold it in static equilibrium. Great, so let's do that and substitute F2 in this equation. So we're going to have 496, so F2 equals to, right, 496.7 newtons equals to 137 multiplied by F1. And from here, you calculate for F1, and F1 is 362.6 newtons. If you divide 496.7 by 137, you're going to get 362.6. And our correct answer is, of course, A, right? It's asking us nearly. Usually on the exam, you're almost all the time you're going to be asked what is most nearly, right? So if you get an answer like that, don't panic, because it's meant to be like that. You have to choose an answer that is closest to the one you got. So 360 is the correct answer. And just a note I want to make is, notice how here F1 is smaller than F2, right? And then F2 is smaller than F3. Where is F3? Have we calculated? Yes. Well, we should go back here and calculate for F3, which we haven't, right? 1177.2. If you were to do that, you know what? I'm going to let you do that. But you're going to find that F3 is greater than F2 and is greater than F1. And it's the way we decided from the beginning, and we knew from the beginning. And it makes sense that it's this way, because if we have friction between the rope and the pulley, imagine if, I'm going to come back to this system here, if we're pulling on F1, if the system goes in this direction, imagine this F1 has to pull F2 along with the friction force that's going to occur here. Because when you pull the pulley in this direction, there is going to be a friction force that is going to occur in the opposite direction. So in order for us to pull force F2, we're also going to have to pull the additional friction force. So that's what happens here. All right, that was it for today, beautiful people. I hope you found this helpful. And if you didn't understand something or you have any questions, please leave your comments in the section below. If you have your FE exam scheduled in the next week or in the next days, I want to wish you good luck. I hope you pass it. If you do, please let me know in the comment section below. Keep practicing the FE problems, and I will see you next week.